Let's get started. Okay, today we're going to be talking about some basic quantum algorithms. So we're going to start off by talking about the Grover search algorithm. So this is, an algorithm developed in the 90s that can be seen as in many ways a prototype for what will appear later. So after talking about the standard Grover search, which has a kind of simple geometric interpretation, we'll show how the ideas developed in that algorithm can be modified to give you a whole host of other algorithms within this framework of quantum singular value transformation, which was developed over the last decade or so. So, okay, let's get started with actually a kind of brief review. So, okay, why are we looking at these quantum algorithms? So, in earlier lectures, those of you who are here will know now that when you would take a quantum state and you evolve it under a generic quantum circuit, it generically becomes very highly entangled, okay? So these quantum states that you get from generic circuits are clearly, beyond the reach of a conventional classical computer. But of course, that's not the end of things, okay? So clearly there's exponential quantum advantage in representing a quantum state, but that's not such a useful task, right? You have to get something out of the quantum state at the end. So you get some highly entangled state. In order to get some information out of it, you have to measure. But as we discussed last time, for a generic state, that measurement is not going to give you very much information. The point is that quantum states are generically locally featureless in that it takes exponential time to extract any useful information from them. So the point is that, although there is a kind of clear exponential advantage in just representing a state, it's very hard to identify exponential advantage. That is to say, a quantum algorithm that performs exponentially better in the problem instance size than its classical counterparts. It's very hard to find, algorithms that have that property, right? In general, our algorithms give us only polynomial speedups, with the exception of, say, Shor's algorithm, which is based on the quantum Fourier transformation, which will not be addressed today. So today, what I'm really going to be talking about is how to construct some controlled paths through the many-body Hilbert space that take you between useful quantum states. Okay. So the classic example that we'll focus on is amplitude amplification. So the problem is basically you're given, you have like a database of bit strings. So B here is just one possible bit string. From this database of bit strings, what you're looking to find are bit strings that satisfy a condition. I'll state generally as 5b is equal to 1, okay? So we want to find bit strings that satisfy this condition called phi. So let me give you a quick example. Let's imagine we laid out our bits in a kind of square array. So say you've got a bunch of bits here. So I've drawn 12 bits here, so there's 4,096 possible bit strings that we need to go through. And what you'd like to do is to find, for example, a set of bits that satisfy a condition you can easily state, right? So maybe you ask, well, if I look at these 3 bits, can I ensure that these 3 bits sum to 1 and 1, 2 would be an example. You could also say that, well, you want to find bit strings that satisfy this condition, but also the condition that the sum of these bit strings is exactly 0, let's say. Or actually, let's say it's 1. Okay, so the point is I can take a bunch of bit strings and specify a bunch of local conditions on these strings, on subsets of the string. Each of these kind of blobs represents some condition I place on the bit strings, with these 2 being examples. And what I'd like to do is basically search through all my bit strings until I find one that satisfies all of my conditions, right? So that's kind of what 5b means. 5b equals 1 means. Any bit string that satisfies all of the conditions specified has 5b equals 1. Otherwise, 5b is 0. So the question is basically, how long did it take to find a bit string satisfying one of these conditions in general? Okay, so let's imagine first off that over all of my bit strings on n qubits, so this thing has length n, here n was 12, over all of my bit strings, let's say that there was only one solution, okay? How long will it take me to find the solution? So yeah, what I'm gonna have to do is go through all of the different possible bit strings and calculate 5b for each of them. And in general, the time it's going to take me to find a bit string that satisfies the condition is going to be 2 to the n, okay? So it takes exponential time to solve this problem. I'm just going to move this back a little bit because I'm realizing I'm out of frame. Okay. So, okay, classically, what we're doing is searching an unstructured database. And the time is going to be of order 2 to the n, okay? Because I have to check each one of them. So what amplitude amplification is going to allow us to do is take this database, and instead of taking time 2 to the n, it's going to take us a time that is square root of 2 to the n. Okay, so we're just considering the overall, we're going from time t to time square root t, so this is only a polynomial speed up. It can nevertheless be pretty significant if you're talking about large databases. Okay, so yeah, so how should we understand the origin of this speed up? How should we visualize Grover search? So one way that I find quite useful for visualizing Grover search is sort of Super Mario inspired. So what we're going to do is we're going to imagine that we start off with our n bits in a superposition of all different configurations. So this here is our initial state, which I'm going to call psi. Okay. So given this initial state psi, I'm realizing I am still out of frame. Okay. Given this initial state psi, what we have is basically saying that each one of our bits is in a superposition of 0 and 1. And we just take the tensor product over these n bits. So the way we can represent this thing is basically to say, well, we've got all these boxes which correspond to the values of the different bits. And we have this row of like n mystery boxes, right? So we have this row of n mystery boxes. Each one of them is like, 0 plus 1. And what we're going to try and do through our algorithm is design a unitary that loads into these mystery boxes the solution, okay? So we're going to apply a unitary such that after we've applied the unitary, what's left here is not just an uncorrelated mixture of zeros and ones, but an in general entangled superposition over the different possible solutions, okay? So for example, what might happen is after you've applied this algorithm, that you have all zeros plus all ones. That would be a solution to a search problem where you were trying to find bit strings such that, all of the b's are equal to each other, right? So the game is, how do we find a unitary that loads the solution into these boxes? So, okay, the basic idea is to perform some pretty unphysical looking reflections in many-body Hilbert space. So the idea is as follows. So we have this function 5b, and we know how to compute it. This thing is 0 or 1, right? So given a bit string, the idea is what we're going to do is we're going to construct a quantum circuit that has the following property. Let's call this unitary R phi. So this is a unitary that has the property that we get minus b. So we have a phase flip, phi b is 1. And we have no phase flip if phi b is 0, okay? So what this means is that we can I call this a reflection. The point is we can write this thing, r of phi, as 1 minus 2 p of phi, where this thing here is like the projection operator into the space of solutions. Okay, are there any questions so far?
We are assuming this, I guess it exists, but are we assuming that like it's easy to construct?
Yeah, right. Good question. So the point is that when I'm here normally you don't place this constraint on yourself, and you just say, well, I have Oracle access to some reflection operator that can do this. Here, what I'm specifying is that our database search problem, just to kind of ground ourselves in reality a bit, I'm specifying that our database search problem is a search problem where phi of b can be efficiently computed. Okay. So the idea is that given a bit string, we know how to compute this function, and then what we can do is construct a kind of classical circuit that evaluates this function given a bit string. Having constructed this classical circuit, which I assume we know how to do, we can then just embed that into a unitary.
Okay.
So I will actually talk in just a moment a little bit more about how you build these things. Okay. So, but I think given that the construction of R phi is very problem specific, I mean, it depends on what our kind of criterion phi of b is. It's going to be much simpler for us to see how to construct the other reflection operator we need, and that other reflection operator will be around the initial state. Okay. So the first thing we need is this thing R of phi, our so-called oracle, which flips the sign of bit strings. Or rather flips the phase of bit strings that are solutions. And then the other reflection operator that we need is going to be around the initial state. So our initial state, which I can write as Hadamard's to the power of tensor n, acting on the all zero state. Okay, so Hadamard here, remember, just takes 0 into 0 plus 1. So this is our initial state. And the other operator I need is going to be this thing R of psi, where R of psi just reflects around psi. Okay, that is to say, if we started off with that is to say, if our state is not psi, or if our state is orthogonal to psi, we get no phase flip. If it is psi, the phase flips by pi. So how do we construct a reflection operator around this state? And then how do we perform Grover search? So first off, let's see how to construct a reflection operator. First, I'll talk about how to create a reflection around this totally trivial product state, right? So the idea here is going to be based on a multiple controlled C0 gate, or a generalized Toffoli gate. So this thing can be constructed just in terms of elementary C0 gates, in fact, a polynomial number of them. But we can represent this C0 as follows. Okay, so what we want is going to be Cn0, and it's going to act on n plus 1 qubits. So here, let's say there are n qubits, and here's the qubit n plus 1. So the multiple controlled C0 does the following. By definition, what this operator does is if all of these input legs, the so-called controls are 1, it applies an X operator here. Okay. So if a 0 comes in here and these are all 1, it flips 0 to 1. And what we're going to use is we're going to convert this multiple control C0 gate into this phase flip without too much difficulty. The idea is pretty simple. So what you do is you just put as your input state here. Zero minus 1. Okay. So let's ask what happens now. So if all of these qubits are in state 1, and this comes in as the minus state, then when we apply X to it, what's going to happen is that we end up with a state that looks like minus 0 plus 1. So if all that is to say, all of these things are 1, our multiple controlled C0 gate does something, And what it does is it flips the sign of this state from 0 minus 1 to minus 0 plus 1. Okay, so we have an overall phase. So just to kind of summarize that point, what I'm saying is that if I want to construct a reflection around the all one state, all I need to do is take Cn naught, acting on, I take basically 1 times n. These are my control keys, these are my controls. Tensor product with 0 minus 1. What I'm going to end up with is an overall flip. Okay, so this just turns into like minus itself. If these control qubits were in any state except for all one, the Cn naught would do nothing. And in that case, I would find a plus sign, okay? So you can see that this C naught acting on this state here is implementing a reflection operator around the kind of all one state, right? So the point then is, okay, well, this thing here, this state, our initial state, is related to the all one state by just a bunch of local unitaries. So just by conjugating this Cn naught by local unitaries, we're going to end up with a reflection around this initial state, okay? So these are our kind of two ingredients in implement as such. And then we get to this kind of nice geometric interpretation of this algorithm. Are there any other questions so far?
Is there a nice way to also construct a reflection operator for R5?
Yeah, right. So that depends. The thing is that depends on the problem instance. So let's see. So yeah, it depends on it. Yeah, because the thing is I have to create an operator that like checks all my 5 variables, right? So I mean the thing is the problem is this depends on how I'm searching the database. Right. So if my criterion for searching the database is, for example, I want to find the bit string where all those bits are in state 0, right? So for that R5, actually, let's do another one. Let's say I'm trying to, because we've just done it. Let's say I was trying to search a database and find the bit string that was all ones, right? So it's a totally trivial search, but you can still see how to construct the reflection around the space. The point is that we just saw it, right? So this is the reflection operator on the all one state. So that would be our oracle operator if we were doing a trivial database search, seeking only the states that happen to be all ones. Another example would be, let's say you wanted to find all bit strings that had the bits the same, right? So then I'd want to find like all ones, or I'd want to find all zeros. In practice, what I'll find is a superposition at the end of the algorithm. And in that case, you need to just construct some, well, okay, I think you can do this with just an extra instead of a qubit. But yeah, the point is that kind of oracle reflection, that depends on the problem you're trying to solve. Okay, so the geometric picture is then pretty simple. So what we have is our two reflection operators, R psi. And we also have a reflection operator around the target space. And so what we're going to do is we're going to imagine decomposing our initial quantum state into a component that's in the target space and not in the target space, okay? So for any psi, what we can do is write, this is the part in the target space, and this is the part not in the target space. So these two parts we can just define in this way. So this is an amplitude, I'm just going to call it sine theta. This is the kind of part where these are the bit strings, yeah, where 5b is 1. Then I have cosine theta phi 0, right? So that is to say phi 0, so psi 0 is just the superposition of all of the bit strings for which 5b was 0. Psi of 1 is the superposition of all of the bit strings for which 5b was 1. These are the kind of superposition of solutions, and this is the superposition of non-solutions. So now I need a few colors. What happened to the pink chalk? There it is. Okay. So here's the idea. So we're going to write our state psi in this two-dimensional space that's just spanned by psi 0 and psi 1, right? That's all we're going to need to worry about. So our initial state psi is here. Psi 0, the non-solutions, is here. Psi 1 is up here. And this is our kind of initial angle relative to the non-solution space. So this is the picture. So what we're going to do is we're going to act, first off, with the reflection around the target space. So when we do this reflection around the target space, it's pretty clear what's going to happen. You know, any component of psi that's kind of in the target space has its sign flipped. So what happens is we get this. Okay? So that's what happens when you act with R phi. Now, having acted with R phi, which is flipped, reflected around the target space, we will reflect around our initial state. Okay? So when we reflect around our initial state, what's going to happen is this thing here, okay, here's our initial state. We need to look at this orthogonal axis. What's going to happen is we flip our state over here. But in fact, it's going to be convenient just for this drawing that we allow ourselves to bring in some global phase change. Of course, this doesn't change anything. So what we'll do is we'll apply minus R of psi, right? So when we apply minus R of psi, what happens is you flip from here over here, and then you flip your sign again, so you end up here. So this is minus R psi. Okay, and if you stare at this for a while, what you can see is that this angle here is just 2 theta. And you can iterate this process. So what's going to happen now is if you take your initial state and you act with the reflection around the target space, and then you act with the reflection around the initial state up to some sign flip, what you do is you just perform a rotation in this 2D space, right? So this is a really kind of simple principle. We're just saying that like 2 reflections form a rotation. Okay, so we do this a few times. And so what we're going to do is define the so-called Grover iterate. Okay. So the Grover's algorithm or amplitude amplification, they're essentially the same thing, just corresponds to acting many times with this operating sheet, right? So all you're doing is performing a rotation in this 2D space. So to kind of state that more explicitly, what we're saying is that given G is minus R psi R phi, if we act with G to the K on psi, which, as you can see from over there, it's sine theta. It is a sine theta and a cosine theta. What you get now okay, so now our aim was to find just the solution to our search problem, right? Our aim was to get all of our weight on psi just into the solution space. So we want to get this thing close to 1 and this thing small. So what we want to choose is that basically 2k plus 1 theta should be approximately equal to pi over 2. That would imply that psi, sorry, G to the K of psi is approximately equal to the solution, where this solution corresponds to a superposition of all the bit strings for which the condition phi b was 1. Yeah, so okay, let's be explicit about that. So this thing here that we're trying to do, we're trying to get to a state where we sum over all sum over all b such that the condition is satisfied. Okay, so in the diagram I was drawing before, what this means is that, okay, we started off with just a like some unentangled superposition over the n bits, where each of our kind of qubits was in 0 plus 1. And now gradually we're building up more and more amplitude until we kind of load into these qubits just a superposition of all the possible solutions. Okay, so this is really all there is to Grover's algorithm. The point is that you can see from here, you should just choose the number of steps to go as like pi, to be inversing theta, to be pi over, basically pi over 4 times theta. So let's now compare that again to unstructured search. So what we've seen so far that if we start in state psi, we're looking to get some solution, psi1, the superposition over all the states for which phi, which our condition phi was 1. What we can do is rotate here in a number of steps that goes as 1 over theta. But remember, you know, our initial state had this structure. So let's imagine for a moment that, you know, we were dealing with a slightly non-trivial search problem where there's not many solutions, right? So in that case, we say that the psi1 in this initial state has a pretty small amplitude relative to psi0. So let's suppose that sine theta is much less than 1, and so it's approximately theta. But now you can see that, of course, sine theta has the interpretation of the amplitude that we just had a solution to begin with, right? So instead of Grover search, let's just for a moment imagine we didn't really make an effort to find our bit strings, right? So the classical approach formulated in terms of a wave function would be to just prepare the initial state, so unentangled superposition of all bit strings, and just look at all of the qubits, right? So if we look at all the qubits, we just get some bit string at random. Having seen that set of qubits, we could then ask, well, is this a solution? Is it not? And probably we're going to find it's not. I mean, the probability that it is going to be, let's see, so if we measure, like the non-quantum approach, it's just like preparing the superposition and measuring all the qubits, which is equivalent to just sampling bits at random. This would give us success with a probability sine squared theta, is the Born probability. And so if we get success with this probability, the number of times we have to repeat our scheme is basically the inverse of this, okay? So that means that the number of repeats in this incoherent measurement-based or essentially classical search is going to go as 1 over theta squared. Okay, so this is the so-called Grover speedup. This is where it's coming from. The point is that if you coherently rotate your state within this space, you can get to your solution space in a number of steps that's 1 over the amplitude rather than 1 over the probability. Okay, so that's the kind of basic idea of Grover search. So if there was one solution, then using this scheme, it would take a number of steps that goes as 2 to the n over 2, whereas here it would take 2 to the n. That can be pretty significant at large n. But now, okay, what we're going to do is leave the 90s and move to the so-called grand unification of quantum algorithms under the umbrella of quantum singular value transformation. So my reason for talking about Grover search in this first part of the class is that we can understand Grover search as a very simple version of a quantum singular value transformation. And so it's going to form a kind of useful way to introduce this pretty abstract idea. So in order to motivate trying to develop more quantum algorithms along these sorts of lines, let me tell you a little bit about the souffle problem. Okay, so you might have already noticed something a bit weird in Grover's algorithm, in that the number of steps that I needed here was determined by 1 over theta, right? What if I just didn't know theta in advance? What if I didn't know how many solutions there were? Yeah, so that's what I'm going to get onto now. Exactly. Okay, thank you for the question. So the way I'm going to motivate thinking about quantum singular value transformations is by talking briefly about something called fixed point quantum search. So fixed point quantum search will solve this so-called souffle problem, which we can understand in the following way. So let's say we're searching a database, but we don't know exactly how many of our bit strings satisfy our condition, right? We don't know how many bit strings solve our problem. So that's obviously the generic case, right? Generically, we can't expect to know, being given some, unsolved decision problem, we don't know how many solutions there are to it. And so if we don't know how many solutions there are to it, that means that we don't know theta. And if we don't know theta, we don't know how many times we're supposed to apply this Grover iterate, right? And so the souffle problem is basically the problem that you can like under or overcook your search problem by going beyond the solution space over here or not going far enough, okay? So the souffle problem is basically that souffles are very hard to cook because you need to time the cooking process properly. So instead of this kind of user-unfriendly search algorithm, which requires a lot of advanced knowledge about how to cook, what we're going to do is construct a search algorithm that has the following structure. So again, we're going to just do rotations in this space. We're going to start, there's going to be, sorry, these are our this is our non-solutions. And these are our solutions. And what we'd like is that if we start with a state that looks like this, that is to say, a state that has quite a lot of weight in the solution space already, then we would like this state to end up basically close to the solution space, okay? Similarly, we would like it if there weren't many solutions, so our initial state is here, that even if there aren't many solutions, we still end up kind of close to the solution space. Similarly, if there are loads of solutions, where's the orange? If there are loads of solutions, again, we would like to end up here. Okay? So this is like solving souffle problem. Okay, and so the solution to this, okay, a pretty elegant solution to this problem. There were previous ones, but what I'm going to talk about now kind of gets all within one method. It's essentially a primitive quantum singular value transformation, or just another early example. And this is some work from Yoda, Lo, and Schwab. And it goes by the name of fixed point search. Okay. So just to be clear on the kind of statement here, so what we should imagine here is that we just have a decision problem we're trying to solve, and we just don't know how many solutions there are to it. Our not knowing how many solutions there are to it, kind of here in this diagram, corresponds to not knowing the angle of the initial state relative to the non-solution space. And what we're trying to do is basically construct an algorithm such that whatever angle this is, so long as it's larger than some threshold, we end up in the solution space. So in order to kind of get to the quantum singular value transformation, I'm going to talk about Grover search in a totally abstract way. I should add, though, that although I'm going to formulate everything I say now in terms of search problems, QSVT is a much more general framework than that. And algorithms such as the linear systems problem, the eigenvalue thresholds problem, and so on, can all be solved also within this QSVT framework. Okay, so here's our kind of abstract view of Grover's algorithm. We had some initial state. Our initial state corresponded to a projection operator like this. Okay, we had some solution space. Our solution space corresponded to a projection operator P phi. We were just trying to take psi, superposition over all bit strings, into the superposition over states for which they're kind of in this space, right? So let's just write down this product of projection operators, right? So this product of projection operators, in a kind of loose way, describes the relationship between our initial space, in this case one-dimensional, and our final space, which is depends on the number of solutions. So from what we've seen so far, we can immediately write down this thing, okay? Superposition over all solutions, normalized, initial state, and sine theta, which is our initial angle. And so what we did in Grover search is we constructed some unitary that had the following property. So this was our Grover iterate to the power of k. We constructed a unitary that did this. Okay, so it looks pretty innocuous, but we just put a unitary in here, and what's happened is that this sine theta was changed to a sine 2k plus 1 theta. Okay, so the point is that if we look at this first line, we can also just view this thing as the singular value decomposition. On the right-hand side, it's the singular value decomposition of this object, right? I'll talk a bit more about that in just a moment. But the singular value decomposition here has some left singular vector, a right singular vector, and some singular value, in this case, sine theta. So when we were doing Grover search, one way of understanding it is that we were constructing a unitary to sit between these two projection operators, defining our input and output spaces, such that the singular vectors were unchanged, but the singular values were changed, right? So this is another SPP. And so what we've done is we've done a transformation of our singular values, right? So this is an early example of a quantum singular value transformation. So this is QSPP example. So the kind of amazing thing, if I can move this out of the way, is that you can go quite a long way by generalizing this idea. So the idea now is, let's say we had these projection operators as written above. And now what we're going to do is we're going to find a unitary to sit between them. Just some unitary, I'm not going to tell you what it is yet, such that we end up with left singular vector unchanged, some function of the singular value, and then the right singular value vector. Okay? And so the kind of amazing thing is that when you do this trick, when you just throw these unitaries in here, it turns out there's an algorithmic way to design any function here that is just an odd degree polynomial of its argument. Okay? So this thing here, some odd polynomial. So we can see this pretty easily in the case of Grover, right? So if we imagine that k was 1, we just had one step, then what we were finding is that we went from sine theta to sine 3 theta. But of course, sine 3 theta can be expressed as a polynomial of sine theta. Okay? So in other words, Grover is the special case where this polynomial okay, I'm going to draw this for very small theta because I don't want to have to convert, but it's essentially doing this, right? Okay, so Grover has these oscillations in it, and so the point is that if we chose theta to be in this sweet spot, we would not overcook, we would get our solution. But if we chose theta to be too far off of this point, say over here, we totally fail, right? We'd over-rotate. So this is Grover. Now the point is that fixed point quantum search basically is an algorithm of exactly this kind, but where you construct the polynomial. So it goes to 1 here, but where you construct a polynomial that looks like this. Okay. Okay, so, but we can actually get even more general than this, right? So I'm just going to claim to you now that there is a way to construct the unitary that gives you this thing. I'll talk about what that unitary is later. But using actually pretty similar operations to what was used in Grover, we're going to be able to switch from this thing to this thing, which no longer suffers from the souffle problem and gives us the rotation described over there. Okay, so QSBT, one way of thinking about it is it's a way to construct routes through the Hilbert space you might not have otherwise expected to be able to access, right? But it is going to require these pretty complicated reflection operators. Okay, so the point here now is that, just to be clear, if theta is larger than some threshold, which over here means that if the angle here is larger than some threshold, we're going to rotate into the solution space. Any questions about this kind of picture so far?
In the Grover search, no matter what theta was, you were eventually going to get to the point where f was 1. But here, if theta is smaller than some critical value, you get stuck.
Sorry, okay, good question. Okay, so theta, we should think of as being determined by just the solution, the problem we're trying to solve, right?
Yeah.
So we picked a problem that has some number of solutions. That number of solutions specifies the value of theta, because that tells us basically the amplitude of our initial state in the solution space.
Yeah.
So the trouble over here was that if we, okay, let's imagine that we designed a Grover search thinking that theta had this value, right? So if we thought theta was here, then, and we designed a Grover search around that, we would end up rotating our state into the solution space. But if really the number of solutions was much smaller than that, and theta was down here, we would not rotate enough. Similarly, if we had more solutions than we thought we had, we would rotate over here. So again, a disaster.
But I guess my point is, no matter what, if you keep doing the unitary rotations defined by the reflections, you would eventually get to the f sine theta equals 1. But here, this doesn't happen. Like with you, can't you just design an f of sine, some f of sine theta that
So I think part of the confusion here is coming from this idea that you can sort of stop your algorithm partway and check if you're there. So you're not allowed to do that. The whole search process is going coherently, and you're only able to look at it at the end. If you look at it partway through, you kind of destroy the coherence and you just start over.
Oh, sorry.
So you have to in advance decide how much you're going to rotate by. Sorry, another question.
So if I have a search problem where I assume my starting vector I'm going to have an equal superposition of all my bit strings, right? So if my search problem has like one solution, I may initially be under the threshold, but if I can like heuristically try like superposition, like a restricted superposition, then like that will increase my theta, right?
Yes, yeah. No, absolutely. Okay, that's a very good point. So yeah, so here we're talking about a totally unstructured search problem, where we have no idea what the solution is in advance. And so our best bet for the initial state is just an equal amplitude superposition over all bit strings. Of course, if you know that the solution is just going to be, say, a bit string where the sum of the bits mod 2 is 0, then you might as well start off with that as your initial state and thereby double the amplitude double the probability that you have a solution. Another question.
Yeah, can you make this f theta as short and fast as possible? The theta star is as small as.
Yeah, okay, great, good question. Yeah, exactly. So the point is basically going to be that this thing is going to consist of a product of many operators. The more so like as you increase the depth of this thing, you can sharpen this thing up. So like similarly in yeah, okay, it's a little bit tougher to see over there. But yeah, the point is that the degree of this polynomial is proportional to the number of steps that you use in order when you're constructing this unitary, as I'll describe in a moment. So the more layers, the more steps, the sharper this thing. And so the more functions you're able to represent.
It sounds like a polynomial.
It's always going to be polynomial, yeah. Okay, so now let's get even more abstract. So what does quantum singular value transformation allow you to do? So let's imagine we are just set in, we're dealing with some n-qubit system, some huge Hilbert space, and let's define two subspaces, which are called the right subspace and the left subspace. Okay, so these are two subspaces of the overall Hilbert space, which has dimension 2pn. The projector here is PR, and the projector here is PL. Okay, so let's take PL times PR, and then it's just a matrix. So let's look at its singular value decomposition. So the singular value decomposition has this form, where, just to be clear on what's going on here, W is a rectangular matrix, sigma is a diagonal matrix, and V is another rectangular matrix. And now W and V are both isometries, meaning that V dagger and is identity, and W dagger W is identity. Okay, sorry, another question for to me.
It says, like, that's a fixed point. It's like, how's that compatible with like unitarity?
Yeah, right. Okay, good question. Yeah, so okay, that's a very good question. It looks pretty confusing. So the point is that okay, we've chosen our initial state already. And we've chosen our and the final state is already chosen, right? The final state is just going to be the projection of the initial state into the solution space. Okay, so the unitary that we design depends on both of these two things. Okay, so the reason it can look kind of nonlinear is because we're actually defining an initial state dependent unitary. And so that's how you get around this apparent violation of linearity. Okay, so general QSVTs. So we've got some output space and some input space. The product of the projectors has some singular value decomposition. What QSVT will allow you to do is put a unitary in the middle of here so that this is transformed by a polynomial. Okay?
Matrix mode.
Yes, it's going to be a polynomial that we should think of as acting like element-wise along this diagonal.
Oh, element. Oh, right.
But yeah, they're the same thing because it's a diagonal matrix. Yeah.
Yeah.
Okay. So yeah, I've just kind of drawn an SVT here, SVD here. But yeah, the point is these are isometries. This is diagonal, and QSVT gives you the way to construct U such that okay. So, this is an extremely general framework, and you can construct a huge number of different transformations in this way. So let's just let me just quickly show you what the unitary over here looks like. Okay, it's pretty similar to what's going on in group research, and there's a pretty intuitive explanation as to why it works. Right. Yeah, we'll wrap up in about 5 minutes. Okay, so Grover search used these reflection operators, right? Now we're going to use these generalized reflection operators. So there's going to be some phase alpha. So this is a kind of generalized reflection operator in that if something is in the left space, you get a phase e to the I alpha. If it's not in the left space, you get e to the minus I alpha. Similarly, we have these generalized reflections around the right space.
Phase alpha was pi over 2 in the original group research.
Exactly. Yeah. So alpha was pi over 2 before. Now we're just playing around with a general alpha. And remarkably, all we're going to have to do is change what alpha is. We're just going to vary alpha and allow it to depend on the number of layers so it depends on the kind of depth. So let's say we choose our unitary to have this kind of structure. So So here we have let's make sure I've got those in the right order. I do not. Okay, so reflect around the solution, generalized reflection around the solution space, generalized reflection around the initial space, and alternate over and over. Okay, so why does this work? So the basic idea, the basic idea is actually pretty simple. So we have this sequence of reflections. Each of them can be written in terms of these projectors. And when you multiply out this product, you get the following. So let's say you just look at the product of PL and PR. So PL times PR, sort of, we already know what this thing is, right? We've defined this thing is, can be expressed as, this is the singular value decomposition by definition, right? But so now let's go on to the next step. Let's say we now end up with another alternating product. PL, PR, PL, PR. And so what we're going to do now is using the fact that these are projection operators, we can write this thing as PL, PR, PR, PL. So I've inserted an extra PR here. PL, PR. Okay? So this is just the emission conjugate of this thing, right? So what we now have is SVD, emission conjugate of SVD, which is just W sigma cubed BN. Okay? So we have these sequences of reflection operators, and what's going to happen when you multiply out this product is you're going to end up with sums over products of projectors in this form, right? So if they're not alternating, of course, that's kind of trivial because PR squared is PR and PL squared is PL. So every term you get is going to end up having this kind of form, okay? Alternating products of projection operators. Alternating products of projection operators of this kind can be simplified through the QSVT, just through the SVD, so that you can see that this thing is just like, singular vectors are the same, and the singular values are transformed. Okay, so let me now just kind of state the final result. This is the kind of intuition as to why it's supposed to work. The actual proof of how powerful this is obviously much more complicated than what we have time for in the next couple of minutes. Statement is, okay, let's suppose we have access to some unitary U. So this is the kind of theorem. We have access to some unitary U that has some matrix A as a subblock in it. Okay? And what we're going to do is locate this A by basically saying that A is PL U PR. Right? So this is a slightly different starting point to what we had before, but you can transform between them with a couple of unitaries. So there's this matrix A that we care about. And what we want to do is act with a singular value transformation of A. Our constraint is that A has to be some block of a unitary that we can act with, okay? And it has this form. So I have to also stress that A can be rectangular. So the idea is that what you do is you construct something called, let's call it U alpha. We construct this thing U alpha, which is just this sequence of generalized reflections conjugated by this initial unitary. And the point is that if this thing U up here had the property that it's so-called block encoded A, and that block encoded A had a singular value transformation of this form, with left and right singular vectors and singular values as usual, then there exists a sequence of alphas, a sequence of these generalized rotations, such that P of L, acting on this new unitary, where F here is any odd degree, any odd polynomial with degree less than or equal to d, and f of sigma less than or equal to 1 for all sigma less than or equal to 1. Okay, this is an extremely powerful framework, right? So given any unitary, then we can just imagine some block of it. Let's say it's a unitary you can actually physically implement. Then just imagine cutting out some rectangular box in the corner of the unitary. That rectangular box is defined by these two subspaces. If you can perform these generalized reflections around these subspaces, then you can use this unitary and those reflections to construct any singular value transformation of A. Okay, so this is a pretty general way to kind of travel around your Hilbert space without ending up in some uncontrollably highly entangled quantum state. Okay, so that brings me to the end. Thank you all for coming along and for their questions. If there are any more questions, please ask them in just a minute or two after I stop the live stream. And yeah, thanks again.